Hi, I'm Shao. In the past parts of this series, we characterized the je ne sais quoi of nice lenses that give a sense of depth, of 3D pop to the images they make. Now, I ran a test using a lot of different lenses with different designs, and came to the conclusion that the addition of a lot of ED glass, low dispersion glass, to the lens design reduces the sense of depth in the images. I know you want to know more about the lenses used in the test, but I'll get to it, I promise. First, let's explore the glass itself. When light passes through glass, its speed is reduced due to the interference of electrons inside the glass with the photons. Now, the angle of the waves of light is also altered, and that depends on the type of glass. The denser the glass, the more reduction in speed, and the higher the change in the angle. Not all light is reduced in speed to the same level. High energy photons, like blue ones, which have a shorter wavelength, are moving faster through the glass than long wave photons, like red ones. So the glass actually separates the light waves or disperses it according to the energy level. The dispersion of light is what causes the dreaded chromatic aberration. Chemically speaking, glass is a solution of silica, soda, and lime. But you can change its optical properties, which are refractive index and dispersion, by adding different substances to it. In general, lighter substances decrease the refractive index and the Abbe number, which is a representation of the dispersion, and heavier substances such as lead, lanthanum, titanium, or zirconium make the glass denser in electrons, increasing the refractive index and the Abbe number. Ideally, you might think you want to maximize the Abbe number, which would give you a very low dispersion optic and a higher image resolution. Extra low dispersion glass is just a glass with a very high Abbe number
of typically 80 and above. This is achieved by adding to the glass very light substances such as calcium fluoride and other fluoride salts. However, the eye is also an optical apparatus, and it has optical properties of its own. Looking at the lens in front of the eye, the Aber number of the eye is about 45, which is lower than almost all optical glass. This means that our naked eye is less sensitive to chromatic aberration than what you might think. As described before, the Aber number or dispersion is tightly linked to the refractive index. And a low refractive index causes an abrupt transition from darkness to lightness, much more abrupt than our vision. Now, to make the transition more natural to our eye, we need to use glass that is of higher refractive index. An important exception to this is enlarging optics. In such optics, chromatic aberration is enlarged too and becomes a limiting factor to the image quality. Now, traditionally, extra low dispersion glass was used in binoculars, microscopes, telescopes, and in some super telephoto lenses. But with the advent from film to digital photography and the increasing resolution of sensors, the typical user of photographic lenses has become more demanding. So camera manufacturers tended to incorporate more and more extra low dispersion glass in the lenses, on the expense of tonal gradation and the natural look of images. Relatively simple optical designs, like this one, have been replaced by computer-generated, highly sophisticated designs like this one.
I would like to introduce you to two fast primes, 40mm lenses. This is the Sigma Art 40mm f1.4, a very precise lens. It's a magnificent instrument for data collection. If I need to collect data for further analysis, like, for example, one of my research studies, where I have to run statistics on the pixels, I will use this one. But then it is quite removed from the natural way our eye sees. This is the Falkland 40mm f1.2. It's a traditional design. It's less sharp, less detailed. Colors are less accurate, but it resembles our vision. Its optical design is similar to the optical design of our eyes. So if I just want to make a pleasant looking image, I will use this one. Look at the size difference. This monstrosity weighs over 1 kilogram. This one is about 1/4 of the weight, and it's much more convenient when you mount it on a camera. I am filming this with Sigma Art. You can see how sharp it is, how precise it is. But then, even in this video, you can probably see that it's a bit flat, a bit lifeless. Now I have switched to the Falklander lens. I hope you can see the difference. It's much more natural looking.
Turns out there has always been a way to reduce chromatic aberration without actually changing the refractive index by much. It involves using complex groups in the lens design. By combining together 2 or more elements with differing directions and differing refractive indices, it is possible to focus light waves with differing energies at more or less the same point. This approach demands a high level of accuracy in production and is perhaps less effective than very high Aber number glass, but it has the benefit of producing a more natural looking image. On the other hand, using too much high density glass with high refractive indices has its own perks. It produces low contrast images. And the appearance of out of focus surfaces looks lumpy or beefy. It's not to everyone's taste. This is typical of the classic Zonar design, which in lenses such as the old Soviet Jupiters. To conclude, there appears to be a right balance between lower dispersion and higher refractive index glass. A good balance will create an image that looks natural, that resembles what we can see with our own eyes. What is this balance then? Well, unfortunately, most lens manufacturers don't advertise the distribution of glass in their designs. But there are a few exceptions. This is the design of a lens that strikes a very good balance, in my opinion. And it contains about 15 to 20% high refraction index glass. So from this and other designs, I can conclude that using about 10 to 30% high refractive index glass is appropriate. The ultimate vindication of my theory would be to take a flat image and by emulating the effects of higher refractive index and higher dispersion, give it some pop. I took the test image made by the Sigma 40mm 1.4 and did two simple manipulations on it. First, I run a selective Gaussian blur only on the red and blue channels, leaving the green channel alone. Then I pulled down the midtones a little bit. After some trial and error, I realized that a very slight Gaussian blur of 1.5 pixels was quite enough. And a higher level of darkening was required. The selective Gaussian blur had an immediate effect on the color of the image. The colors looked deeper, more satisfying, I think, although color is always subjective. The resulting image looked a lot more poppy to my eyes. I would give it a score of about 3, maybe, in the scale I created. Comparing it to the original image taken with lens 2, which was the Falkland 40mm lens, the images are surprisingly similar. And remember, I did not change anything in the white balance or color balance. Emulating the effect of some light dispersion was enough to make the images quite similar, which shows that my hypothesis is probably correct.